Hello my friends, and welcome back to the You Can Do TV channel. Across the open landscapes between Jasiniec and Patnau, the construction of the 400 kV transmission line represents a critical upgrade to Poland's high-voltage power infrastructure. Massive reinforced concrete foundations are installed to anchor steel lattice pylons designed to withstand extreme wind loads and long conductor spans. Once cured, tower sections are assembled on-site and erected using heavy cranes with strict control of geometry and alignment to maintain electrical clearances. After foundation completion, steel lattice pylons are assembled and erected using large-capacity cranes, allowing precise placement of tower sections even in constrained terrain. Each lift is carefully sequenced to maintain structural alignment and design tolerances. Once the towers are secured, conductor installation shifts to the air. Helicopters are deployed to pull pilot lines across long spans, rivers, and environmentally sensitive areas where ground-based methods are impractical. These pilot lines are then used to draw in the full-size high-voltage conductors under controlled tension, minimizing ground impact and reducing installation time. The aerial stringing process ensures accurate routing and protects both the conductors and surrounding infrastructure. With the conductors in place, specialized crews move along the lines using purpose-built equipment, such as suspended trolleys and harness systems. Working directly on the cables, technicians install spacers, dampers, and fittings, while also adjusting sag and alignment to meet strict electrical and mechanical specifications. These mobile platforms allow safe, efficient access across long spans at height. Every stage is governed by rigorous safety procedures and continuous monitoring. The result is a high-capacity 400 kV line engineered for long-term reliability, creating conditions for deriving power from renewable and conventional sources. Platform powerline work with Blackcomb helicopters is a discipline reserved exclusively for elite specialists. Only highly trained pilots and certified line workers are qualified to operate in this environment, where every maneuver carries inherent risk. Loads are suspended beneath helicopters operating inches from live structures, with no margin for error. Wind shifts, rotor wash, dynamic load swing, and limited visual references constantly challenge stability and precision. A single miscalculation can endanger personnel, equipment, and critical grid assets. To manage these risks, operations rely on rigorous flight planning, redundant safety protocols, real-time communication, and exact execution. This is high-consequence construction at its most demanding, where expertise, discipline, and experience are the only safeguards against failure. In the rugged terrain of Guerrero, Mexico, moving gold ore from the El Limon open pit to the processing plant required a transport solution capable of overcoming a 400-meter elevation drop. In 2016, Minera Media Luna selected Doppelmayr's RopeCon system to meet this challenge. The installation follows a carefully engineered alignment across steep slopes, minimizing ground disturbance while maintaining high operational safety. Once in operation, the RopeCon continuously conveys up to 1,000 metric tons of ore per hour over a distance of 1.3 kilometers, delivering material directly into the valley. Designed with strong environmental and safety performance in mind, the system replaces conventional haulage routes with a controlled, energy-efficient transport process optimized for demanding mining conditions. The manufacturing of a hybrid wind tower is a carefully sequenced industrial process that combines the mass and stiffness of concrete with the height efficiency of steel. Production begins with the concrete lower tower, where high-strength concrete is cast into large precast segments or rings using precision steel molds. Each segment is reinforced with dense rebar cages and integrated ducts for post-tensioning tendons. After curing under controlled conditions, the segments are demolded, inspected, and prepared for transport. At the same time, steel upper tower sections are fabricated in parallel. Heavy steel plates are rolled into cylindrical shells, welded longitudinally and circumferentially, and subjected to non-destructive testing to verify weld quality. Surface treatments and protective coatings are applied to ensure long-term corrosion resistance. On-site, manufacturing transitions into assembly. Concrete segments are stacked vertically with cranes, aligned with millimeter accuracy, and post-tension to form a single monolithic structure capable of resisting high wind and fatigue loads. Once the concrete section reaches its design height, the steel tower sections are lifted and bolted on top, creating a seamless transition between materials. Internal platforms, ladders, cable systems, and access components are then installed. Final inspections, dimensional checks, and structural verification complete the process. The result is a hybrid tower optimized for modern wind turbines, manufactured through parallel production, precise quality control, and engineered integration, enabling greater hub heights, improved performance, and efficient use of materials. Building the world's largest offshore wind foundations is a highly sequenced industrial process where precision governs every stage. Production begins with heavy wall steel plates up to 150 millimeters thick, bent into circular segments and welded internally and externally using double submerged arc welding. These sections are joined into multi-section pipes that form the primary structural elements. Attention then shifts to the transition piece, the interface between foundation and turbine, where deck plates and massive girders are installed to distribute loads. Specialized marine coatings are applied to protect the structure from corrosion. Below, enormous legs connected by X-braces are assembled into lower and upper jacket sections. Once joined, the full jacket reaches 94 meters in height and 200 tons in weight. Final loadout operations transfer the completed structure directly from the quay, ready for offshore installation. Before offshore wind can power cities, an unseen battle of scale and precision unfolds at the harbor. Rising nearly 94 meters, equal to a 30-story building, and weighing an immense 200 tons, each fixed offshore wind jacket from SK Ocean Plant defines world-class engineering. This milestone marks the beginning of exporting 52 colossal substructures to Taiwan, each designed to support a 14-megawatt turbine. Shipped methodically, 3 jackets per loadout over a 14-month campaign, these steel giants depart step by step, laying the foundations of a new energy era at sea. 200 kilometers off northwestern Australia, the mooring operation for Shell's Prelude enters its most critical phase. Weighing 660,000 tons when fully loaded, Prelude is the largest floating facility ever built, designed to withstand cyclones and extreme offshore conditions. At the heart of the system lies a massive internal turret, allowing the vessel to weather vane freely with wind and waves. Beneath the hull, one of the strongest mooring systems ever engineered takes shape. 16 enormous chain legs, each connected to piles drilled deep into the seabed. The operation focuses on hauling in pre-laid chains link by link using giant winches, guided by precise engineering calculations. Tugboats hold the facility steady while loads are monitored in real time. As predetermined golden links lock into position, structural tension is achieved. With the 8th mooring line secured, Prelude becomes storm-safe, anchored for decades of continuous operation at sea. Constructing a conical grain silo floor is a demanding concrete operation where geometry, timing, and surface control must align perfectly. In this project, the challenge is defined by scale and slope. A 38-degree incline, spanning 58 feet across and rising 34 feet from bottom to peak. Such angles place extreme demands on both material behavior and finishing accuracy. The process begins with precise formwork and reinforcement installation, engineered to maintain shape and structural continuity under the weight of fresh concrete. Once placement starts, controlling slump and flow becomes critical to prevent segregation or slippage on the steep surface. This is where the Lura Lightning Strike roller screed transforms complexity into efficiency. The roller screed moves steadily across the cone, compacting and leveling the concrete in a single continuous motion. Its rotating drum applies uniform pressure, ensuring consistent thickness while drawing excess material downslope. This controlled action produces a dense, well-finished surface, even on severe inclines that would challenge traditional screeding methods. As the pour advances upward, crews maintain rhythm and coordination, keeping the screed aligned while monitoring surface tolerance. The result is a smooth, structurally sound conical floor, designed to channel grain efficiently toward the silo outlet. What appears effortless is, in reality, a precise execution of equipment, material science, and technique, turning one of concrete's hardest jobs into a clean, repeatable process. Deep below the Mersey Gateway site, construction of the south pylon begins inside a circular excavation supported by timber retaining walls. Within the shaft, a dense reinforcement cage forms the structural core of the foundation. Over the 3rd to the 4th of August 2015, concrete pumps delivered 400 cubic meters of concrete in 200 loads during a continuous 24-hour, 45-minute pour, completed ahead of schedule. Scaffolding and pumping systems operated in tight coordination. The mass concrete foundation will require around 90 days to reach full design strength, creating a stable base for the pylon above. At Wind Park Koningshovener Hohe, the installation of the hybrid tower system marks a defining moment in modern onshore wind construction. Developed by Max Bogle, the hybrid tower combines precast concrete segments in the lower section with a steel upper tower, delivering greater hub heights and improved structural efficiency. Executing this system demands extreme precision, especially during assembly at height. Installation begins with the casting and curing of massive precast concrete rings, each engineered to tight tolerances. These segments are transported to site and stacked sequentially, forming the lower tower. Post-tensioning cables are then installed and stressed to create a single, load-bearing concrete structure capable of resisting dynamic wind loads. As the tower rises, one of the world's largest mobile cranes takes over. With immense lifting capacity and reach, the crane positions the steel upper tower sections with millimeter accuracy. Each lift is carefully planned to account for wind conditions, load sway, and ground pressure. Once secured, the nacelle and rotor components are hoisted and mounted, completing the turbine structure. The hybrid system reduces material usage while increasing height and performance. At Königshovener Höhe, the synchronized interaction between prefabrication, heavy lifting technology, and precise assembly showcases how advanced construction methods are redefining wind energy infrastructure at scale. On the open plains of Wieringermeer, a new generation of wind power takes shape as a GE 3.6 to 137 turbine rises against the Dutch sky. This installation is not simply about erecting a machine, it is a carefully sequenced engineering operation designed to deliver reliable, utility-scale energy. The project centers on a tubular steel tower with a hub height of 131 meters, engineered to optimize wind capture in Class IIB conditions with an average wind speed of 7.5 meters per second. Each stage follows strict technical logic. Tower sections are lifted and aligned with millimeter accuracy, forming a rigid backbone capable of supporting extreme dynamic loads. Above, the nacelle houses a 3.6 megawatt generator, upgraded to maximize efficiency and grid output. The blades, each stretching 67.2 meters, are installed with controlled crane operations, creating a total rotor diameter of 137 meters. This vast swept area is the key to the turbine's performance, enabling an annual energy production of up to 14.9 GWh and a capacity factor approaching 47%. Noise emissions are carefully managed at 106 dBA, meeting regulatory requirements while operating close to communities and public infrastructure. Once commissioned, this single turbine is capable of supplying clean electricity to households, hospitals, and public institutions. The result is a precise combination of structural engineering, aerodynamics, and power systems, proof that modern wind technology can scale up without compromising efficiency, safety, or reliability. Malaysia's first large-scale floating solar project under the LSS2 scheme marks a significant technical milestone in renewable energy deployment. The 12.995 MWP photovoltaic system at Dengkil, Selangor, spans 53 acres of water surface and integrates 38,790 photovoltaic panels mounted on more than 67,000 engineered floaters. The floating configuration naturally cools the panels, improving electrical efficiency while eliminating the need for valuable land resources. At the core of the system is a robust anchoring and mooring design, engineered to maintain stability under changing water levels and wind loads. Carefully planned cable routing, enhanced electrical insulation, and water-resistant components ensure operational safety and long-term reliability. With simplified access for maintenance and optimized installation costs, the project delivers 16,640 megawatt-hours annually, powering thousands of homes while demonstrating the technical and economic viability of large-scale floating solar solutions. Sustainable rehabilitation of Germany's L213 demonstrates how advanced materials can extend pavement life while maintaining traffic flow. Along the 5.7-kilometer corridor, the deteriorated concrete roadway, marked by cracks, deformations, and repeated patching, was milled and overlaid with a new asphalt surface reinforced by HCXP. This high-performance PVA asphalt reinforcement grid was engineered to delay reflective cracking and withstand permanent dynamic traffic loads. Its alkali resistance allowed direct installation over both concrete and asphalt, while exceptional installation durability minimized damage during paving. By splitting the reinforcement layout, continuous local access to Nistorf was preserved. The result is a safer, longer-lasting roadway with reduced maintenance demand. The jointed, unreinforced concrete pavement constructed in Slipform is executed under a strictly controlled and sequential process to ensure long-term durability and performance. Construction begins with precise preparation of the subbase, which is carefully graded and leveled to meet the required design elevations and alignment coordinates. Once approved, ready-mix concrete is transported to the site by dump trucks and transferred into the Slipform paver hopper using an excavator, ensuring a continuous and consistent supply. As the concrete is placed, integrated internal vibrators within the Slipform paver provide automatic and uniform compaction, achieving the specified pavement width and thickness. Primary surface finishing is carried out by the paver screed, producing a smooth and even profile. This is followed by manual steel screeding to correct minor surface irregularities and enhance overall flatness. After finishing, the pavement surface is brush textured to improve skid resistance and traffic safety. A resin-based curing compound is then applied to prevent rapid moisture loss and promote proper hydration. The surface is subsequently protected with appropriate coverings to safeguard it from environmental influences. Finally, transverse and longitudinal joints are saw-cut within 24 hours of placement to effectively control shrinkage cracking and ensure structural integrity throughout the pavement's service life. The Guerrero GP 2400 Slipform paver was deployed on the I-29 project in Sioux City, Iowa, demonstrating high productivity and precision in concrete paving. Designed for versatility, the GP 2400 can place up to 24 feet of concrete in a single pass while maintaining excellent surface smoothness and grade control. On this project, the machine handled demanding highway specifications, delivering consistent slab quality and efficient output. At Boley Park Station in Chelmsford, the surface installation follows a clearly defined construction sequence. As part of a £250 million rail investment, multicolor-colored asphalt is selected early to meet both structural and visual requirements. The asphalt is produced with integrated pigmentation, ensuring consistent color through the full layer depth. During paving, separate zones are laid to create clear, visual demarcation for footpaths, cycle lanes, and bus lanes. Once compacted, the surface delivers high durability, low maintenance performance, and long-term color stability. BAA accreditation confirms its suitability for road use, supporting a sustainable transport network serving 14,000 new homes. Rising above the River Mersey, the Mersey Gateway stands as one of the UK's largest infrastructure projects, reshaping connections between Runcorn and Widnes. Stretching 2.3 kilometers in length, the cable-stayed bridge features a 1-kilometer main river span, supported by 3 pylons. The tallest tower reaches 125 meters above the riverbed, anchoring 146 cable stays that progressively draw the deck together. From the air, immense cranes and bridge-building machines dominate the site as deck segments advance and gaps begin to close. Designed as a 6-lane tolled crossing, the bridge is set to open in autumn 2017, delivering faster, more reliable journeys across Halton's key transport corridor. VSL played a decisive technical role in the construction of the Petrovsky Bridge, a key link within St. Petersburg's western high-speed diameter, by delivering and installing the stay cable system and executing complex heavy lifting operations. The steel-concrete composite deck was supported using advanced VSL stay cable technology, engineered for durability and precise force control. "15 massive bridge segments, each weighing 142 tons, were prefabricated on land, transported by barge, and lifted into position using VSL SLU 40-strand jacks. The lifting system achieved a vertical travel of 30 meters at a speed of 26 meters per hour, allowing each segment to be installed in just 2 hours. An optimized 13-day cycle enabled fast-track construction. Structural performance was enhanced by 100 VSL friction dampers, 16 load cells for continuous cable force monitoring, and 12 stay cable ties. With 1 stay cable installed per day, VSL's integrated lifting and stressing system delivered speed, accuracy, and long-term reliability for this landmark bridge. On Mexico City's Autopista Urbana Sur, massive prefabricated girders become the backbone of a new elevated highway. Each trabe, weighing up to 420 tons, is engineered with millimetric precision before arriving on site, where next-generation cranes with lifting capacities of up to 200 tons take over. The assembly sequence is meticulously planned. Alignment, controlled lifting, rotation, and final placement onto columns, all completed in as little as 16 minutes per girder. Nearly 1,000 of these elements will form 21 kilometers of continuous roadway. Prefabrication ensures strict quality control, while advanced lifting technology minimizes on-site risk and disruption. This complex operation showcases Mexican engineering expertise, delivering a modern urban artery that combines speed of construction, structural reliability, and long-term value for the city. On the Cusi-Marmara motorway, the ILM-3 bridge advances span by span using the incremental launching method, a construction technique engineered for precision and repetition. Each cycle begins at the casting yard, where reinforcement steel and post-tensioning ducts, up to 45 tons in the first stage, are installed into the formwork. Internal molds are then closed, followed by the first concrete pour of approximately 280 cubic meters, forming the initial deck segment. After curing, the formwork is opened and reconfigured. Upper formwork installation, internal mold extraction, and cantilever reinforcement assembly prepare the structure for the second reinforcement phase, which adds roughly 65 tons of steel and PT ducts. A second concrete pour of nearly 480 cubic meters completes the segment, high-strength tendons are threaded and stressed, locking structural capacity into the deck. Once post-tensioning is completed, hydraulic jacks engage the deck and push it forward, along sliding bearings. The superstructure advances at a controlled rate of roughly 5 meters per hour, covering up to 55 meters, in a 10-hour operation. Each launch cycle spans approximately 8 days, transforming raw concrete segments into a continuous bridge deck. This method minimizes false work, maintains geometric accuracy, and enables efficient construction across long spans with limited ground access. Precasting the bridge deck for the St. Croix crossing is a highly controlled process, driven by structural efficiency and balance. The bridge adopts an extradose design, combining box girder construction with cable-stayed principles, resulting in a deck composed of hundreds of hollow concrete segments. Each segment weighs roughly 170 to 180 tons and is engineered with internal voids to reduce weight while maintaining strength. Construction begins once piers reach full height and crossbeams are completed. At each pier, a cast-in-place pier table is formed using custom molds shaped to match the precast segments. Reinforcement steel and high-strength tendons are installed, followed by concrete placement, creating a precise interface for segment erection. Deck construction then advances outward using balanced cantilever methods. Segments are delivered by barge and lifted into position using segment lifters or a high-capacity ringer crane. Epoxy is applied between segment faces for shear transfer and sealing before segments are post-tensioned together. Crews alternate placement on both sides of each pier to maintain structural equilibrium. Once spans are closed, internal cable systems distribute loads back to the piers and foundations, forming a stable, long-span bridge deck. Beneath the calm surface of the St. Croix River, an immense engineering effort quietly shaped the future St. Croix crossing. Crews installed steel casings through a prefabricated work platform, advancing them through water, deep muck, sand, and soft sandstone to reach bedrock. Inside each casing, material was excavated while water remained in place, followed by drilling an additional 25 feet into solid rock. Underwater concrete seals, cofferdams, and reinforced footings transformed these shafts into permanent caissons, forming load-bearing foundations designed to support hundreds of thousands of tons with long-term structural stability. In the harsh desert landscape of Rajasthan, delivering water depends on a precisely executed pipeline installation process. The 210-kilometer Barmer raw water pipeline connects Nachna to the Barmer refinery, supplying the water required for cooling, steam generation, and chemical operations. Installation begins with detailed route surveying and trench preparation across sand dunes and rocky ground. Large-diameter steel pipes are positioned, aligned, and welded section by section, followed by non-destructive testing to ensure joint integrity. Protective coatings and cathodic systems are applied to resist corrosion in extreme conditions. Once installed, the pipeline is carefully backfilled and pressure tested before commissioning. Despite intense heat and shifting terrain, Mega Engineering delivered a continuous, reliable water corridor, an essential system supporting energy production and long-term sustainability in one of India's most demanding environments. Railway track renewal is a highly synchronized engineering operation designed to restore structural integrity, ride quality, and long-term performance, with minimal disruption to rail traffic. The process opens with the unloading of new continuous welded rails, delivered in precise lengths and staged along the corridor to match the renewal sequence. Existing fastening systems are then systematically removed, releasing the worn rails and sleepers while preserving the ballast foundation. A specialized track renewal train becomes the core of the operation. This integrated machine advances steadily along the line, extracting old sleepers and rails in a continuous flow while preparing the formation for new components. Degraded sleepers are lifted out and conveyed away, immediately followed by the accurate placement of new sleepers at exact spacing and alignment. Old rails are removed, section by section, making way for new rails that are positioned with controlled geometry. To create continuous rail strings, flash butt welding is performed on-site, joining rail ends under high pressure and temperature. The resulting welds are ground to precise profiles, restoring a smooth running surface. Recovered old rails and scrap metal are collected and removed for recycling, keeping the worksite clear and efficient. Track de-stressing follows, a critical step that sets the rails at a neutral temperature to prevent buckling or fracture under thermal loads. New fastening systems are then installed, locking rails and sleepers into a stable structural unit. In locations requiring localized joints or repairs, aluminothermic welding is carried out to achieve high-strength, durable connections. With the rail structure secured, fresh ballast is unloaded to replenish material lost over time. Ballast profiling shapes the stone to support sleepers evenly and ensure proper drainage. Precision track leveling machines correct vertical and horizontal alignment, restoring design geometry for speed and comfort. Track brushing cleans excess ballast from the rail zone, preparing the line for final consolidation. Dynamic track stabilization completes the structural work, simulating the effect of thousands of train passes to rapidly achieve long-term track stability. Throughout the operation, site logistics coordinate material supply, waste removal, and machine movements with minute-by-minute accuracy. The result is a renewed railway corridor, capable of supporting higher speeds, reduced maintenance, and improved safety, delivered through an industrial-scale process where every step is engineered for precision, efficiency, and durability. High-speed rail leaves no margin for compromise. As train velocities push beyond 350 km per hour, the infrastructure beneath the rails must deliver absolute precision, durability, and long-term stability. In Austria, PORR has answered that challenge with the Slab Track Austria system, developed in cooperation with OD as a next-generation solution for high-performance rail corridors. Each track slab is factory-produced under controlled conditions using high-precision casting methods to achieve consistent dimensional tolerances and exposed concrete quality. An integrated elastic separation layer is installed beneath every slab to reduce structure-borne vibration, mitigate stress concentrations, and allow vertical settlement regulation if required during service life. Standard slab dimensions are approximately 5.16 meters in length and 2.4 meters in width, though custom geometries are possible. Slabs are transported directly to site and positioned using portal cranes or track-based installation equipment. achieving placement accuracy within plus or minus 5 mm. No intermediate storage or rehandling is required. Track alignment is finalized during installation, eliminating the need for post-correction measures. A self-compacting, high early strength grout concrete is then poured beneath the slabs, ensuring full contact without vibration and preserving track geometry. The system enables rapid construction during short possession windows, supports fast component replacement, and maintains structural integrity even under derailment scenarios, making it a robust solution for modern high-performance rail infrastructure. The construction of the Stousbahn funicular followed a meticulously engineered sequence to conquer unprecedented steepness. Work began with extensive surveying and alignment planning to replace the old 1933 line with a straight 740-meter route climbing, 744 meters of vertical gain. Groundwork focused on cutting through rock and unstable ground, requiring the construction of 3 tunnels with gradients up to 110% using a drill and blast method and specialized drilling devices designed for steep inclines. Track supports were anchored directly into the mountainside, and prefabricated rail sections were positioned with precision to maintain safe and exact geometry. Haulage and counter cables were installed and tensioned along the entire line, with hold-down rollers preventing cable lift at steep points. Final stages included installation of rotating, cylindrical passenger cabins that automatically keep floors level throughout the gradient, along with rigorous testing of cable traction, braking systems, and safety controls before opening to the public in December 2017. Pekabek's prefabrication represents a highly industrialized construction model in which precision engineering, repeatability, and speed converge to fundamentally redefine how large-scale buildings are delivered. Rather than relying on traditional, labor-intensive site work, the Pekabek system shifts the majority of construction activity into a controlled factory environment. Within this setting, structural concrete elements are manufactured under tightly regulated conditions, independent of weather, seasonal limitations, and many of the uncertainties that typically affect on-site construction. The process begins long before any physical production takes place, with detailed digital design and planning. Advanced structural models define the geometry of each element, including reinforcement layouts, lifting points, embedded components, and connection details. These digital models function as the backbone of the entire production process. Once finalized, the data is transferred directly to the factory floor, ensuring that every operation follows exact specifications. This seamless integration between design and manufacturing allows dimensional accuracy to be maintained from the first mold adjustment to the final assembled structure on site. On the production floor, steel molds are prepared with extreme care. They are thoroughly cleaned, inspected, and adjusted to precise tolerances. These reusable molds enable the casting of wall panels, columns, beams, slabs, staircases, and complex facade elements with consistent geometry and surface quality. The use of rigid steel formwork ensures repeatability across hundreds or even thousands of identical components, a key advantage of prefabrication in large-scale residential, commercial, and industrial projects. Reinforcement fabrication follows as a critical stage in the process. Steel cages are assembled strictly according to structural calculations and design documentation. During this stage, anchors, sleeves, conduits, inserts, and connection hardware are integrated directly into the reinforcement. Every assembly is inspected before placement to verify correct spacing, cover depth, and alignment. This step is essential, as the reinforcement defines the load-bearing capacity, durability, and long-term performance of each concrete element. Concrete production is handled by on-site batching plants, optimized for consistency and performance. Mixed designs are carefully engineered to achieve the required strength, workability, and curing characteristics. Precise dosing of cement, aggregates, water, and chemical admixtures ensures uniform quality across every batch. Once the concrete is poured into the molds, vibration systems are used to compact the material, eliminating air voids and achieving a dense, homogeneous structure. Surface finishing is performed immediately after casting, producing smooth architectural finishes or textured surfaces depending on project requirements. Curing takes place under strictly controlled conditions within the factory. Temperature and humidity are regulated to accelerate strength development, while minimizing shrinkage, cracking, and internal stresses. Compared to conventional cast-in-place concrete, this controlled curing environment allows prefabricated elements to reach design strength more quickly and consistently. As a result, production cycles are shortened without compromising structural performance or durability. After demolding, each prefabricated element undergoes rigorous quality control procedures. Dimensions are measured, surfaces are inspected, and the placement of embedded components is verified against design specifications. Structural integrity is assessed to ensure compliance with applicable standards and project requirements. Any non-conforming elements are corrected or rejected before leaving the factory, preventing costly delays and rework on site. This systematic quality assurance process is one of the defining advantages of prefabrication, delivering reliability that is difficult to achieve with traditional construction methods. Logistics and handling represent the final phase of the manufacturing process. Each element is clearly labeled, documented, and stored in a planned sequence corresponding to the installation schedule. Transport planning accounts for weight, geometry, and lifting requirements, ensuring safe and efficient movement from the factory to the construction site. When components arrive on site, they are ready for immediate installation, significantly reducing on-site labor, crane time, and dependency on favorable weather conditions. Through this comprehensive manufacturing process, Pecabex demonstrates how modern prefabrication delivers speed, accuracy, and consistency at scale. Structural elements arrive on site as finished products rather than partially completed work, transforming construction into an assembly-based operation. The result is shorter project timelines, predictable costs, and structures engineered to perform exactly as designed. In this model, construction no longer begins in the field. It begins on the factory floor, where quality, efficiency, and precision are built into every element from the very start. In June 2012, at the exposed entrance of Great Yarmouth Harbour, Precision Marine Engineering was put to the test. Sheet Piling UK Limited was commissioned to construct two circular cofferdams at the outer breakwaters, under strict conditions that demanded completion by the end of August and minimal disruption to live harbor traffic. Fast-flowing tidal waters left no margin for error. To meet these constraints, an innovative pre-assembly strategy was adopted. Each cofferdam was fully fabricated on the adjacent quay, built around a robust temporary support frame. Straight web steel sheet piles were carefully interlocked and monitored to control pile creep, allowing the circular cells to close without inducing structural strain. Once complete, each 400-ton cell was lifted by a shear leg crane barge and floated into position using GPS-controlled marine positioning. After touchdown on the seabed, 8 660mm tubular piles were vibrated 5 meters deep to anchor the structure. The sheet piles were then driven to final tow level, followed by hydraulic sand infill. Both cofferdams were installed within a single week, without interrupting harbor operations, marking a first for tidal cofferdam construction in the UK and meeting the contract deadline ahead of schedule. Jinan Investment's agricultural developments are built on an engineering-first approach that transforms arid terrain into high-efficiency production systems. Each project begins with detailed land surveying and geotechnical assessment, enabling precise grading, controlled compaction, and engineered drainage that protects soil structure and long-term productivity. Water management is the central technical pillar. High-capacity pumping stations, reinforced pipeline networks, and precision-controlled center pivot irrigation systems deliver water exactly where and when it is needed, dramatically reducing losses from evaporation and runoff. Integrated automation and monitoring systems regulate pressure, flow rate, and application timing, lowering energy consumption while maximizing crop yield. On-site manufacturing of polymer irrigation pipes ensures consistent quality, pressure resistance, and rapid deployment, reducing dependency on external supply chains. Mechanized planting and harvesting systems are calibrated for uniform output and continuous operation at scale. The value of this engineering-driven model is measurable: higher yield per hectare, reduced water and energy consumption, lower maintenance demands, and predictable long-term performance. Through technical discipline and system integration, Jinan Investment delivers agricultural infrastructure that converts scarce resources into sustainable, high-value production capacity. At the edge of modern engineering, power takes physical form. The Ape Octagon stands as the world's largest vibratory driver extractor, a machine built to move foundations once thought immovable. Final assembly was completed in April 2011, marking a major milestone in heavy construction technology. Following assembly, the Octagon underwent full-scale testing on a production-size pile, proving its capacity under real-world conditions. Manufactured in the United States and shipped to China, the hammer was assembled for one of the most ambitious infrastructure projects ever attempted, the Hong Kong-Zhuhai-Macau Bridge, the largest bridge project in the world. Designed to handle piles up to 22 meters in diameter, 40 meters in length, and weighing 450 metric tons, the Octagon delivers an extraordinary 40,000 kilonewtons of driving force. With an eccentric moment of 1,340 kilogram meters and power output exceeding 7,100 kilowatts, this machine represents precision, scale, and coordination at the highest level of global construction.